I think, oh, geez, something is going on here. I don't know what's going on. Okay. All right. Okay. I always like to start with a little bit of a recap and just try to give us the big picture, right? So Monte Carlo methods, we have some kind of probability distribution or some kind of probability-based problem, and getting the answers that we want often involves some challenging math, integrals or something like that. And the Monte Carlo method says, you know what, I can get at least an estimate of the answer that I want by just drawing a sample from the distribution and then applying the function to it, okay? And so in the beginning, we started off with, how do we draw random samples? And we had inverse CDF, we had rejection sampling, and convolutions and stuff. And so that gave us the ability to draw independent samples, samples that were IID from a distribution, okay? Then we applied Monte Carlo integration, Monte Carlo estimation, importance sampling, and those are ways to estimate the values of functions that have been applied to a distribution. Okay, so you've got a random variable x, and you want to say, what's going to be the expected value of a function applied to that random variable? Well, what we do is we draw random samples from x, apply the function to those things, and apply and take the average of those values. Okay. And importance sampling said, well, what if you can't draw from x and you have to draw from g instead? And we had ways to accommodate for that, and then ways to kind of estimate an integral and things like that. Okay, so that's kind of where we've been so far. And and then last week I just barely touched on some Bayesian concepts. Okay. Because those will come into play later as far as an application of all of these Monte Carlo methods. Okay. Today we're going to go back to Monte Carlo methods. Okay. So last week was just kind of the lecture on Bayesian topics. We're going to go back to Monte Carlo methods, and then later on we'll meet up again with the Bayesian concepts. Okay. And so, okay, so just kind of a recap. All right, so Monte Carlo methods. Okay, so basically to avoid difficult math, we use random samples. As a stand-in for a random variable. Okay, so we learned how to draw IID guess values. From distributions, and that's inverse CDF and rejection sampling. And then we learned how to estimate the expected value of a function applied to a random variable. Okay, and that's Monte Carlo estimation, Monte Carlo integration, and along with importance sampling. Okay, and then we had some introductory Bayesian concepts. Basically the prior, the likelihood, marginal, and posterior. Okay, today we will go back to Monte Carlo methods. Okay, and then we'll introduce Markov chains. Okay, so so what is a Markov chain? Why are we going to learn Markov chains? The idea here is, you know, when we're dealing, so you know, so far all of our examples have basically been one-dimensional. We did a little bit of bivariate normal, but pretty much all of our examples have been one-dimensional. And when you have a unidimensional distribution, these, you know, IID methods of drawing from a distribution, they're rather straightforward. Okay, inverse CDF, rejection sampling, that's all fine. Okay, as we get into more complex problems, we might have higher dimensional distributions to sample over. And the methods that we've covered so far become very inefficient in terms of getting the samples that we want. And so a Markov chain, we will use kind of these concepts of Markov chains to get us samples. Okay, the key difference though is that our samples are no longer IID. They're no longer independent of each other. With a Markov chain, each sample that you draw is dependent on the previous value that you drew. Okay, and when something is dependent, then the math all changes and things get messy. But you know, thanks to some proofs and theorems that, you know, we're not really going to get into the deep theory of this. Basically, the proofs show that you can use Markov chains that are dependent, where the values are dependent on each other, to basically and use them in the same way that we did and Monte Carlo estimation and integration. Okay, we can take those values, apply a function, and get an estimate of what we're looking for. Okay, the Markov chains are much more efficient at covering a high-dimensional or, you know, kind of a very sparse probability space. Okay, so let me just kind of boil that down into a few words here, and then I'll kind of illustrate the idea. Okay, so introduce Markov chains. Okay, so you know, our current methods of getting a random sample do not work well in high dimensional problems. Okay, Markov chains are more efficient but produce samples that are not independent of each other. Okay, but this is okay. All right. Can I flip over? Okay, so we may have, so in high dimensional problems, what's going on here? Okay, so in high dimensional problems, kind of the probability space might be very sparse. Okay, and what that means is almost everywhere the probability is very close to zero. Okay, so in most places, and only in a small pocket is, you know, the probability, you know, of interest. Okay. And in the homework, you might have seen the difference. So the homework you just turned in, you had importance sampling, okay? And you did the same integral calculation or estimation versus the previous week where you did Monte Carlo estimation or integration where you drew from the uniform distribution, right? So the homework, 2 homeworks ago, you drew from the uniform, and then this past homework, you drew from a normal distribution that was kind of truncated to fit, that looked a lot more like the distribution of interest. And the hope was that you saw that by drawing from the normal distribution and using that to estimate the integral and the values, you saw that your values converged, your estimates converged a lot faster, right? We saw that, okay? And so you could imagine a probability space, and for now we can just picture, you know, a space where, like, here, I'll just do a univariate example, and we'll just say we'll have a normal distribution, okay? And the normal distribution technically goes from minus infinity to positive infinity. And so, you know, if I just go from like minus 50 to plus 50, what does the distribution look like? So if I go from minus 50 to plus 50, the distribution is pretty much 0 everywhere, right? It's like 0, 0, 0, 0, 0. And then only around like, from like this small gap from -3 to +3, is there actually any anything of interest, right? I don't even know how to draw this here. Okay, everywhere else, it's pretty much, it's not 0, but it's very close to 0, right? So this is the normal distribution. This is just kind of a univariate example. And let's say you tried to do Monte Carlo estimation where you're drawing from, I don't know, the uniform distribution from -50 to +50, okay? Your values here, your estimate will converge very poorly, right? Because pretty much everywhere you draw a value at, you know, -35 and +10 and all of these things, you're drawing all these values and the estimate is going to be very close to 0, okay? And then it's only when you get in this kind of this small region of like 6% of your values do you get anything of interest, okay? And so, you know, Monte Carlo estimation here where we draw x from, let's say, uniform -50 to 50 will give, you know, very poor estimates. For a long time, because the values we draw will have probabilities close to 0 for, you know, most of the most random values. Okay, does that make sense? Okay, and this is just an example, a univariate case, and you can imagine, what if we had a bivariate normal, okay, and we're so in the univariate case we've got about between from -3 to +3, so that's about 6% of your values, okay, and in the bivariate now you know, your space goes from -50 to +50 in 2 dimensions. And it's only 6% in each dimension, and so of the total space for a bivariate case, I don't know why my computer keeps doing this to me. Okay, in the bivariate case, it's just basically you have this tiny little mound, and you know, everywhere else is pretty much flat, right? And so in this case, you know, only about 6% of values are relevant, and then here only 0.06 times 0.06, what's that? 0.0036 of the values will be relevant. And that's if we go from -50 to 50. Okay. Conceptually, does this make sense? What I'm talking about when I'm talking about a sparse probability distribution? Okay, and the problem just gets compounded when we get into higher dimensions. Okay, and it's not uncommon to have a problem with 50 dimensions or something like that. And in that probability space, everything, only a tiny, tiny, tiny pocket will have values of interest, and everywhere else has probabilities very close to 0. Okay? And so, kind of the method of drawing IID values using, like rejection sampling or something like that, just will be too inefficient for it to be of use for us. Okay, and so we need to have something better. Okay, and that's where the Markov chains come in. Okay. So Markov chains allow us generate a sample drawn from the probability distribution in a kind of much more efficient way. Okay. Your x of i's are no longer IID from f of x. Okay? They're no longer independent. And instead, kind of the picture is that you draw x1, and this leads to x2, and this will lead us to x3, and so on and so forth until you get to your x of n, okay? So this would be, and the Markov property is that x sub I is dependent only on the previous value. Which we might say is x at I minus 1. I'm going to change all of these from subscripts to supers. I apologize. So x at time I x at time I is dependent only on the previous value, x at time I minus 1. Okay, and so that's the Markov property. Okay. And we'll start off kind of with some basic examples, but the idea is we want to set up a Markov chain so that when we keep drawing values from the Markov chain, the resulting values will be reflective of the distribution that's of interest to us, okay? And so we want to design a Markov chain so that the values x sub I drawn from the Markov chain will be equivalent to drawing values from the probability distribution of interest. Okay, which we will call our target PDF. Okay. So, we're gonna set up a chain, and to draw values from a chain, we'll talk about what all that means. But basically, we're gonna have some kind of rules for how to generate values. Okay, and these rules for generating values will depend on our current value, okay? And that's what makes it a Markov chain. So we start off with a current value, we follow the rules for generating the next value, we get a new value, and we go, okay, let's look at the rules for generating the next value. And we just keep doing that. We're gonna get a series of values, and the hope, or the idea is that after we do all of these values, by following these rules of generating values according to the Markov chain, the resulting values that we got are equivalent to having drawn them from the target PDF, okay? So, so far, our previous methods of drawing from the target PDF is like, okay, this is what the PDF looks like. We're gonna do this thing, inverse CDF. We're gonna do rejection sampling, and we're gonna get values that way, okay? And we, generate things from the uniform at first or something, and we do stuff. Here, we have a different system for generating values, but the idea is that at the end of the day, the values we've generated still work, okay? They're no longer independent. We look at our current value, we follow the rules, we get the next value. Then we use that value, we follow the rules, and get the next value, okay? So, okay, so Markov chains. So we're gonna start off with discrete space, discrete time Markov chains, which is kind of like your most basic example, but it works. Markov chains are defined by what's called a transition matrix or transition kernel. It describes how to take your current value and transition to the next value, okay? So, Markov chains are defined by a transition matrix, or for discrete or transition kind of kernel for continuous. Transition kernel, okay? These are instructions for getting the next value based on the current value. Okay, these are instructions for getting the next value based on the current value, okay? And we will use this. We use this to generate values from a Markov chain. Okay, and again, the idea is we're no longer drawing values IID from our target distribution. We're drawing values according to the transition matrix or transition kernel of the Markov chain. And this, at the end of the day, will produce values that come from the distribution, okay? From the target, we draw . or okay, I'll say draw values according to the Markov chain okay, and these values end up being drawn from the target PDF. Okay. And so this, Markov chain Monte Carlo stuff ends up being a very useful tool because it allows us to kind of attack these super high dimensional problems with, complicated parameter spaces of high dimensionality and allow us to get an answer that, in a reasonable amount of time, okay? So you can imagine some kind of problem with, 20 dimensions, right? And all of our regular analytic approaches are too hard to do. We can't do the integrals, 20 dimensions, I don't know, it's too complicated. We can't do it that way. We want to say, okay, well, let's do a Monte Carlo method. And, if we just throw one of our current methods at this 20-dimensional problem, it might be working for hours and hours and hours and will give us really terrible estimates because the probability space is so sparse, okay? A Markov chain will run in a shorter amount of time. It might still be a few hours, but it'll run into a shorter amount of time and give us much better estimates because it is drawing values a lot more efficiently, okay? And so we're going to start off with the easiest or the smallest possible version of this, which is going to be called the two-state Markov chain, okay? So the smallest possible version, and in real life, we would not go through the trouble of setting up the Markov chain for a two-state case because the two-state case we can do very easily ourselves using the traditional methods, okay? But we'll have the two-state Markov chain just to kind of illustrate these concepts of the transition matrix and all of this stuff, okay? Okay. So you can think of a probability distribution where you have basically two outcomes, right? Heads or tails or something like that, okay? And if we think of a probability distribution where you have heads or tails, with a coin, we generally think of all of those values being IID. Every time you flip the coin, it's independent of what has happened in the past. That's fine, okay? Again, with the Markov chain, everything is no longer independent, and so maybe a better case will be, maybe like the weather or something like that, okay? It doesn't really matter, but the idea is here we've got two states. We'll have state A and state B. And if you are at state A, you might transition to state B, or you might transition and remain at state A, okay? And likewise, if you're at state B, you might transition and move to state A, or you might remain at state B, okay? And so we will have a matrix to represent this. Okay, so we'll have your current state, A and B, and here's the next state, A and B, and I don't know. I'm just arbitrarily throwing some numbers here. right? So if you're at A, you might return to A with probability 0.7. You might go to B with probability 0.3. If you're at B, you might go to A with probability 0.4, or you will remain at B with probability 0.6. Okay, and this could be something like, you know, A is, it is sunny, and B is not sunny. So maybe that means cloudy or rain, snow, etc. Anything other than sunny. Okay, and so, you know, if you are at A, maybe you stay at A or go to B. And if you're at B, you know, likewise, and vice versa. Okay, and the Markov property here is that where you are, your next state depends only on your current state. So you don't look at what has happened in the past, you're just looking at where you currently are, and that will determine where you go next, okay? Kind of our memory lessonness. Next state depends only on our current state. Okay, and so basically, you know, we would just start at some arbitrary state, maybe A, and then we would go, okay, let's see, do we stay at A or do we go to B? You know, you draw something, and maybe you get another A. You say, do I stay at A or do I go? And then, and you just keep kind of going around, and then maybe you end up at B, and at B, I don't know. And you kind of get some kind of state like this, right? Some kind of sequence like this, and you just let this run. And in the end, you'll have a whole bunch of A's and you'll have a whole bunch of B's. And the distribution of A's and B's will eventually, what we will converge to its stationary distribution, okay? So you start here, you let it run, just according to this. You say, you know, where am I? I'm at A. I will stay at A with probability 0.7, I'll go to B with probability 0.3, so on and so forth, okay? Or you say, where am I? I'm at B. Maybe I'll stay at B with probability 0.6, or I'll go over to A with probability 0.4, okay? And you just do this, you let it run, okay? And then, as you let a Markov chain run, the values from the Markov chain will eventually converge to its stationary distribution. Okay, you know, I'll say if the chain meets kind of ergodic properties. right? Okay, and this is what we want is we want a Markov chain that eventually reaches its stationary distribution. The stationary distribution is where all of the states are in balance, okay? And it's kind of like when you know, in our two-state case, it's when we're at equilibrium, when the probability of going from A to B is equal to the probability of going from B to A, okay? And so let me just kind of introduce this concept of kind of ergodic theory. And this will be kind of just a loose definition, not non-formal definition. Okay, which is basically if a Markov chain is irreducible and aperiodic, then no matter where you start, the kind of the values drawn from the chain will converge to its stationary distribution. Okay, irreducible means you can get to any state irreducible means you can get to any state from any other state. Okay, so if we have a chain, you know, a bunch of states, state A, state B, state C, state D, like this, this is irreducible because if you are at state A, you can eventually get to state D. Okay, you can get, there is a path exists from every state to every other state. It might not be a direct path, but you can get there, right? And it's kind of like in North America, every city is kind of connected, right? Like like wherever you are, you can take a car and you can drive to any other city in North America because it's connected by roads, right? We're not connected to like Japan. You can't drive a car to Japan. Okay, you gotta get in an airplane or boat. But okay, and it's a little different because that's a network. But this is kind of the idea of a state, is that if you're in this state, you could eventually end up in another state, right? If you are currently rich, you could make a series of bad decisions and end up homeless, okay? And then there's debate, but is it possible for a homeless person to become rich? We'd like to think yes, and so in that case, the idea of being able to go from one state to another state is irreducible, and that wherever you are able to reach something else. Okay, if you have something like this, okay, this would be irreducible, but then okay, this is no longer irreducible. Okay, because if you are at D, there's no way for you to get to A, right? So you are no longer able to get to another state, you know, based on where you are. So part of it is that the Markov chain has to be irreducible. Okay, it has to be able. You have to be able to reach every other state from any state. Maybe not a direct path, but there needs some kind of path needs to exist. Okay, and then let me define aperiodic. Okay, so maybe I'll define periodic and say aperiodic is the opposite of that. Okay, a chain is periodic if certain states are possible only at certain times. So for example, if you have some silly state like this, okay, then your chain will go A, B, A, B, A, B, right? There's no, that's it, okay? And so, you know, A's are only possible on, quote, the odd states, and B is only possible on the even states. Okay, so that would be periodic. Okay, aperiodic means any state can appear at any time. All right, and on, you know, practically speaking, if it is possible to go from a state back to itself, then the chain will become aperiodic. So if you just add this, if it's possible to go from A back to A, then it becomes aperiodic. So now both A and B can appear at, you know, odd or even times. Okay, so that's the concept of irreducible and aperiodic. And the ergodic theory or ergodic theorem says if you've got a chain, Markov chain, that is irreducible and aperiodic, eventually it will converge to its stationary distribution. Did you have a question, Alejandro?
Yeah, so in this case it looks like for the secondary example, when you say periodic by any time you need, it doesn't matter whether it's odd or even, but in theory, would you argue that it's still periodic in the sense that A can only come after B or after itself? Wait, no. I don't know, it feels kind of weird because the way you defined it earlier was just that you have to have them in certain places, but in this case, when you have B, there is no other outcomes. You can't have B again after itself.
Yeah, but that's okay. Like if we had a different chain, like B could show up, at time 15, or time another chain B could show up at time 16. It doesn't have to be that B has to show up at time 15 and show up at time 16 during the same chain. But it's saying, like, if somebody else ran it, B could show up at time 16 or whatever. It could show up at these other times. Okay, kind of in the long run. It's practically speaking, a chain will be aperiodic if just one of the states has the ability to kind of go back to itself, because you can kind of use that one state as a way, I don't know, holding pattern or something, so that the things can shift around and stuff. You just don't want a state where things have to follow a certain pattern, okay? And things only happen during the summer or the winter or something like that, okay? It's if it's periodic, then this theory doesn't hold. Okay. All right, and so the back to the ergodic theorem is that if a chain is irreducible and aperiodic, okay, we can say the chain is ergodic. And that means an ergodic chain will eventually converge to its stationary distribution, okay? The stationary distribution is achieved when all of the states, are in equilibrium, okay? Which means basically the probability of entering that state is equal to the probability of leaving that state. Okay, so if for the two-state case, okay, this means the stationary distribution means that if we are at A, the probability of going from A to B is going to be equal of moving from B to A. Or and you feel like, oh well, this is always true. But if you are this is true only at equilibrium. Okay, so this is true, or during the stationary distribution. Okay, when you're not at the stationary distribution, this is not true. Okay. So let me just kind of illustrate this in our two-state case. So we have A and B. Okay, in our we had 0.3 and 0.7 and 0.4 and 0.6, right? This is current, this is next. Okay. So let's just say we begin with kind of, we'll say 100% of the population at A. Okay, we'll begin with 100% of the population at A. And so I can kind of represent this with a vector and put in 1.0 and 0 here. Okay, and then and I'll have my transition probability matrix P, which will be 0.7, 0.3, 0.4, and 0.6. Okay, and we can use this, the transition matrix, to see the distribution at the next state, or at the next time. Okay, so we're going to start off with 100% of the population at A. So after one transition, after one time, what do we have? We got, in the next phase, how many do we have at A? 0.7, right? And then 30% of the people at A will have moved to B, right? So if I do the matrix multiplication, I get 0.7 and 0.3, okay? We are not at equilibrium because basically of the entire population, 30% moved to B, and how many went from B to A? 0, right? And so we are not at equilibrium, okay? And then we can see, all right, well, what would happen at the next phase? Okay, so at time t equals 2, I can do this. And what will we have? So we'll say A to A will be 0.7 to 0.7. I'll just do 0.7 times 0.7 is 0.49. And B to A will be 0.3 times 0.4, 0.12. And then A to B will be 0.7 times 0.3, 0.21. And B to B will be 0.3 times 0.6, 0.18, 0.39. And so at time 2, we've got the distribution is 0.61 and 0.39. Okay, and we're not at equilibrium because the amount going from B to A is 0.12, and the amount going from A to B is 0.21. Okay, so we're not at equilibrium. We're not at our stationary distribution yet. Right? But by using the transition matrix, we can kind of see the next value that we're gonna, or the distribution at the next time, right? Is this okay? So what will be true at the stationary distribution? So we often call the stationary distribution is called pi. And this is kind of the distribution where the states are at equilibrium. And it will have the property that the stationary distribution pi times our transition matrix P okay, if I do pi times P, what should it equal? If everything's at equilibrium, it will just equal pi, okay? Meaning that after applying the transition matrix, everything remains the same, because even though things may have moved around, everything stays the same. And so, here is our transition matrix P. Our P is equal to 0.7, 0.3, 0.4, 0.6. Okay, and in our case, our stationary distribution will be 4/7 and 3/7. It basically just comes down to balancing out A to B and B to A. Okay, so if this was A and B and A and B, it's A to B and B to A. We have 0.3 and 0.4, and if we normalize those to be 1, we would end up getting 3/7 and 4/7. Okay, and so if I multiply this by this, and we say, okay, how much will go from A to A and A to B and things like that, everything ends up being equal. So if we say, all right, so A to A will be 4/7 times 0.7 plus B to A, which will be 3/7 times 0.4. Okay, so I get 4/7 times 0.7 is what's that? 2.8 over 7, and over here I get 1.2 over 7 for a total of 4/7. Okay, and then here we got A to B, which is 4/7 times 0.3, and B to A, I'm sorry, B to B, 3/7 times 0.6. This ends up being 1.2 over 7, and here I got 1.8 over 7, and this also totals out to be 3/7. So what we see is that pi, our stationary distribution, multiplied by our transition matrix P, ends up having the same distribution afterwards, okay, of being of pi, 4/7 and 3/7. Okay, so at this time, so if the population has this distribution of 4/7 and 3/7, after we apply the transition matrix, it still has the same distribution, 4/7 and 3/7. Okay, and so we say when our chain has reached this point, it has reached its stationary distribution, because applying the transition probabilities don't affect the resulting distribution. Okay. Okay, and so again, the kind of the ergodic theorem says that if the chain is irreducible and aperiodic, then no matter where your chain begins, the distribution of the chain will eventually converge to the stationary distribution. Okay, so the idea here is that we can start with an arbitrary kind of initial distribution, and if we keep applying the transition matrix, we will get the stationary distribution. Okay, so basically if I start off with some vector representing our initial distribution over states, and I multiply it by our matrix P, and I do this many times, so I'm going to multiply it by P to the n, eventually this converges to the stationary distribution. So is that okay? For the two-state case, okay, if P has these probabilities, P12, P21, and P22, then your stationary distribution pi will be P21 over P12 plus P21, comma, and over here P12 over P12 plus P21. All right, so let me just kind of do something silly. We'll just illustrate this on, we'll just multiply matrices in R, and I'll just show you that it does converge. Oh, what's going on? Okay, so let's say our distribution will be, we'll start off with okay, so D, this will be our, oops. What am I doing? Matrix 1, 0, number of rows equals 1. Is my R broken? Okay. Something is wrong. Jeez. Okay, let's try this again. All right, so we'll make a matrix P, and what do I have? I've got 0.7, 0.3, 0.4, 0.6. Number of rows equals 2 by row equals true. All right, so let's just take a look at P. Okay, that's what we want. Our distribution D is matrix C 1, 0, number of rows 1. Okay, and I've got D. Okay, so if I do D multiplied by P, this is the distribution at the next step. Okay. So I'm going to just do this over and over again. Okay. So so we can just see what this looks like. If I multiply it by P again, then we have 0.61 and 0.39, which is, we did the first two by hand. And if I do this again, then I get 0.583, 0.417, and then as I keep applying this, you can see eventually the values don't change very, very much, right? 0.5714311 and 0.5714286. Let's see. So at this point, it looks like we've reached convergence here, okay? And we can kind of compare this to, what is 4 over 7? It's exactly that. And what's 3 over 7, right? And it's exactly that, okay? I can start off with a different initial configuration. I can start off with everyone at state B, okay? So I can start off with 0 and 1, and I can apply the transition matrix P, okay? And after one phase, I will be at 0.4 and 0.6. Then after 2 states, it becomes this. After 3, and we can see, again, we reach a point of convergence here. Okay, and so, and no matter what we have as our initial distribution, as long as it is an initial distribution that adds up to 1, right? So I can start off with half and half, and I just keep applying the transition matrix, and it converges, okay? All right. Okay, so I mean that's just a silly example with the 2 states, right? And and what does this look like in practice? Basically, we would just be drawing values here, and in this 2-state case, it's a little silly because it just feels very unnatural. Is that the stationary distribution of this Markov chain, the Markov chain defined by our transition matrix P here, has this stationary distribution over the 2 states. Okay. And so in a roundabout way, if you wanted to generate samples of, let's say, coin flips or something, where it has a probability of landing heads 4/7 and a probability of tails landing 3/7, you could use this transition probability matrix P to keep generating values, okay? They will not be independent values, but overall the values you've seen at the end of the day will be distributed in 4/7 heads and 3/7 tails or something like that. And that's kind of the idea that we're going for here, is that we're going to design a chain so that its stationary distribution is equal to the distribution that we desire. Okay, and so we start off with a two-state case. We'll work up to a slightly more complex case, and then we'll get to kind of our algorithms here. Okay. All right. So one idea that we have. What time is it? It's 11:30. Okay. So I'm going to introduce the concept behind the Metropolis algorithm. We probably won't get into the nitty-gritty yet. Is that we're going to design a Markov chain that will have a stationary distribution. That's the one that we want, okay? So the Metropolis algorithm. Okay, so this is an algorithm that tells us how to create our, transition matrix. Okay, or transition kernel. Okay, algorithm that tells us how to create our transition matrix or kernel so that the Markov chain defined by this transition matrix, so that the Markov chain will have a stationary distribution equal to our desired target distribution. Okay. All right, and the rule is simple. Okay, maybe I'll start with the rule, and then we'll apply it to an example on Thursday or something. Okay, and this is the rule. It says you are look at your current state, and then propose transitioning, maybe I'll just say propose moving to another state. Okay, propose moving to another state. And then we have rules about the proposal. The proposal needs to be symmetric. We'll talk about that in a moment, okay? Okay. So you look at your current state, right? You're at this state, and then you say, maybe I'll go to another state. Okay, you propose moving to another state. And then you will either go to that state or you won't, okay? And this is how you decide, okay? So at the next time interval, we will either stay put at the current state, or move, transition to the proposed state. Okay, and whether we decide to move or not, so we will move, move with the probability equal to the probability of the proposed state divided by the probability of our current state. Okay? And that's pretty much it, okay? So we're at our current state. We say, maybe I want to go to another state. And on our next turn, we're either going to go there or we're not, okay? And we will go there with this probability. The proposed state, probability of the proposed state divided by the probability of the current state. Okay? And if this probability is greater than 1, then you go there with probability 1. Okay? You can't go with probability greater than 1. You just go with probability 1. Okay? So, okay, that's the Metropolis algorithm, right? And if you define your transition matrix according to this rule here, the resulting Markov chain will have the target distribution, okay? What is the target distribution in the first place? Well, the target distribution, I should say, is what defines the probability of the proposed state in the target distribution divided by the probability of the current state in the target distribution. Okay, we will move with probability. It's probability of proposed state, I guess, in target PDF, and probability of the current state in the target PDF. Okay, and if you use your target PDF to decide to figure out these transition probabilities, then the resulting Markov chain will converge to its stationary distribution, and its stationary distribution will be the target PDF. Okay, so let's, I guess we'll start off with this example from the textbook. Okay, so this example comes from the textbook doing Bayesian data analysis. You guys had homework problems from that textbook, and I don't know if you guys did the reading from that chapter. It's the book has like dogs on it, right? And it's great, right? You guys get the PDF for free with the link in the syllabus. Yes, okay. So I think it's an excellent textbook. And I'm going to just follow the example that they used to introduce the Metropolis algorithm, which is we're going to have our desired distribution is our target PDF. And so we've got, so this is chapter 7, doing Bayesian data analysis. Okay, and we've got a nation of 7 islands. Okay, and politician, we've got a politician that wants to campaign on all the islands, okay? Okay, and he wants to visit each island according to its population. Or in our case, the population is kind of a proxy for probability, right? If we were to draw someone randomly from the island, which island they come from would be proportional to the population of the island, okay? He wants to visit each island according to its population, and the island's populations will just be proportional to its island number. Okay, so basically the target PDF, or in this case PMF, is this. The probability of island 1 is 1 over 28. The probability of island 2 is 2 over 28. Probability of island 3 is 3 over 28, so on and so forth. Probability of island 6 is 6 over 28, and the probability of island 7 is 7 over 28, okay? And you can see that this would add up to a probability of 1, okay? Because if we do add up 1 through 7, we get 28. And so this is this is his target PMF, okay? Target distribution that we want. But we're gonna pretend that it's easy to sample directly from this distribution, but we're going to pretend that we can't. And so instead, we're going to design a Markov chain so that the resulting Markov chain will have a stationary distribution equal to the target distribution. Okay, so we will design a Markov chain okay, using the Metropolis algorithm okay, we'll design a Markov chain using the Metropolis algorithm, and if we do that, then the Markov chain stationary distribution will be equal to this target distribution, okay? The Markov chain stationary distribution will equal the target distribution. And what that means is that we can get a sample that is drawn from the target distribution by running the Markov chain instead of trying to do IID samples, okay? Although in this case, drawing IID samples is very easy to do, right? But we're using these as kind of examples on simple examples to show how the Markov chain works so that we can do the complicated examples where we can't do our IID samples. Okay, so how do we apply the Metropolis algorithm, right? Okay, so the Metropolis algorithm. The Metropolis algorithm for the island hopping. Okay, so we will just start on an island. Okay, this will be our current state. Okay, we will propose going to another island. Okay, and so our proposal needs to be symmetric. For the Metropolis algorithm, the proposal needs to be symmetric. I'll explain this fully, but just for now, a simple proposal will be this. I will flip a coin. Okay, if heads, I propose, so we'll say our current state is theta. I propose going to island theta plus 1. Okay, so if I'm at island 3 and I flip heads, I'll propose going to island 4. Okay, and if tails, I propose going to island theta minus 1. Okay, so if I'm on island 3 and I flip tails, I'll propose going to island 2. Okay, is that all right? Okay, and then if we're on one of the end islands, like the biggest island is island 7, okay, and there's no island 8. Okay, so if I'm on island 7 and I flip heads, then what we'll do is we'll pretend like I'm proposing going to island 8 that just doesn't exist. Okay, and if I get tails, I would propose going to island 6. If I'm on island 1 and I get heads, I'll propose going to island 2. And if I get tails, I'll propose going to island 0, which also doesn't exist. Okay, so we can propose going to island 8 or island 0, which do not exist. Okay, so we've proposed going to an island. All right, then we have to decide, do I actually go to the island? Do we go to the island? All right, well, we have to figure out this transition probability. Okay, the transition, or maybe we'll call it the acceptance probability. I don't know. Do we go to the island? So we'll say we go with probability equal to basically the probability of the island, of proposed island, in basically the target PDF, divided by the probability of current island in the target, in target PDF, PMF, okay? Which in this case would just be, we want to go with something proportional to its population. So this will just be the population of proposed island divided by the population of the current island. Okay, is that okay? One thing about using the population rather than the probability is that the probabilities have a normalizing constant. We put 1 over 28, 2 over 28, and things like that, so that the whole thing adds up to 1. Okay? If we just use the population, we don't actually have to calculate that normalizing constant of 28 in the bottom. We can just say the population is an island of 1,000, island of 2,000, island of 7,000, or something like that. Okay, I think we've run out of time. We'll definitely continue this on Thursday. Okay, so we'll see you then.